Can you see my screen? Anyone?
Yes.
Right.
Yes.
So we are really lucky in the States because of all the natural gas that we have and all the solar energy that we have, especially in that quarter, but also because of the wind energy, right? So we have huge area that's basically under really favorable wind condition. This tornado alley basically is also a really good for the for the wind, especially if you go high enough, like 8 meter, and that's not a big deal because those wind turbine 50-meter diameter is nothing, right? So the fact that you're gonna be hanging the X of the turbine is at 8 meter, that is typical. That's not a big deal. So you can see all that area, and especially when you go to Oklahoma, our panhandle is really very good place for it. And as I told you before, BSO, the public service company of Oklahoma, the one that generates electricity for us, they really wanted to have a wind farm over here, big wind farm, and they wanted to run the cable, but they didn't get the right permit to be able to do this. But they're gonna make money by building this, and a lot of jobs too. Okay. And actually, one of the previous students that we had in the class, he's actually working on wind energy, but in his station in Florida now. So hopefully one of you may end up working in wind energy too. And actually, if you go over here, if you're going to Dallas, you will see a lot of wind farms, especially near the waterfalls that we had south. You'll see all of them over there. So I don't know what happened to the quality. This used to be colored. I don't know what happened this time. But this map was showing that on top of the velocity over here in this tornado alley, you can get even higher velocity offshore. Okay, so if you go a little bit in the water, you'll get even higher velocity. But people don't like it to basically be in their beach house. And I remember, even as I told you, Senator Kennedy, Ted Kennedy, which was supposed to, he's supposed to be really like a green senator, like he would love renewable energy. When they wanted to put a wind farm in the back side of his own state, he refused. He declined. So people, amazingly, and from environmental point of view, sometimes they complain about wind turbine. Okay, there is legitimate complaint about noise, for example, and if it's like nearby and whoosh, whoosh, you don't want to hear this. And there are some concern also about maybe electromagnetic interference. There's also real concern about this thing kill birds, and especially bats, and especially some endangered bat species. But there are research about how we can scare bats from getting through them. You need to or color it so that the birds can see this thing, rather than making blend with the sky. So there are ways to basically scare birds from getting closer to it. Okay. But what I'm trying to say that it's not like totally the silver bullet that solve our energy. And actually, just today, I saw the Department of Energy. If I posted this in my Facebook account actually. If I can find it, they actually show the prediction for the future, and they are saying that solar is actually gonna exceed wind in the US. So here it is. So this is where we are, right? And you can see how like solar is tiny compared to wind, right? And all those renewable energy is really nothing compared to natural gas and coal and nuclear. You can see how nuclear is kind of stagnant. And actually, this year is the largest retirement in nuclear asset in the US. They're gonna retire 2 power plants. We are building one new. But the point is, look at the future. So the future is solar is really, so by the time you guys will retire, maybe in like 30 years, you will retire with solar energy actually more than the wind. That is the prediction. Kind of hydro, kind of hard to grow, right? Because kind of like they build all the dams in the US. But maybe your company can still build turbines somewhere else in Africa and China and South Asia, right? But anyway, so the wind are going to grow, but not as much as the solar. That's the prediction. So other places in the world, they actually have a lot of wind. I mean, this is the places where they have offshore wind turbine, not onshore, but offshore. Those are wind turbines sitting in the water. And you can see how basically here in Europe they have so much, we have only one. And it was just this, if you Google this Block Island farm, right? It just like maybe the last 2 years or something start to run. It's not really that old. While Europe have so many. And I mean, you could argue that, well, because our natural gas is so cheap, why would we invest in a big wind farm, right? And maybe that is true. So I guess the natural gas is our blessing and our curse at the same time. But you can see how much wind farm is actually sitting in Europe over there. So they have 5 wind farm, sorry, 5 turbine in that guy. Okay, compared to, you can see how much in each one of those wind farms. And recently people even start and build floating wind farm. So what's the difference between floating and fixed? Those one are sitting in the ground, so they cannot go that far deep. But if you make them floating, then you can send them very back into the ocean, away from your beach. So you win 2 things by doing this. One, you get away from the people that say, I don't like a wind farm in my beach. I just want to see the ocean and the waves. Well, if it's far enough, they don't have to see it. They don't have to listen to it, right? And second, the farther you go, the more velocity you'll get because you get away from the interference of the buildings and the cities on the shore. So Japan actually built 2, I think, like a few years ago, in the place where they had the nuclear accident. So in front of their Fukushima nuclear reactor that exploded, they had 4 reactors over there, right? They actually build farther down in the across, basically a floating wind turbine. It's still experimental, but the point is you can put it there and it can generate electricity. And of course, you have a cable that will take you from there to here. Okay. I also, one of the students in this that had this course in the past actually work for a company that work as a supplier for this company. So they build machines for this one. See, look at this boat. This boat come near the wind farm, the turbine that you want to fix, and it's basically dig its feet down and it anchor itself to the ground, and then it can actually take the plate, replace it, even replace the generator. So you need a ship like this to surface the farm. So it's a lot of engineering design to build this to be able to surface all those turbine plates. Okay, this is just an artist impression. This is not real, but this is real. Not the whole farm, but a floating wind turbines are real, right? Very good. So the here is the tower. The tower is here, and here is where the generator is sitting, and that generator is probably heavy, right? And from that generator, there's a cable that run all the way down so that you can connect to the consumer. And of course, this tower with the generator move to face the wind. So if the wind is coming this way, they go this way. If the wind's coming that way, they go that way. But because this thing is heavy, it does not like bounce immediately like the American farm windmill, the small one that has big tail, and the tail always take it to the right place. This move very quickly, but this one will move very slowly. This one move with a gear. There's a gear and a motor, and there is a sensor that basically say, well, the wind is coming from the east now, and so they slowly move to face the east. But because of the cable that's running, they cannot basically like wind themselves too much. So they just have to go this way and then this way. So if you want to go more than that, you have to go from the other way, right? And the velocity triangle, as always, is valid still. V wind coming all axial at the inlet. Again, when the wind is blowing toward you, there is no way for the wind to come with a twist. It just come all axial. And I'm just having a cross section here. This guy, of course, when you extrude it from the page, is going to be really deep, right? As deep as like maybe 50 meters. And so the wind would come at like this, and he would move up, and that make V relative plus U plate equal V wind. And I had a homework problem where I will basically show them the velocity triangle, and I say plot the plate for me. Okay, and then I will say if this was a fan, not a turbine, plot the plate for me. So what's the difference? So if it's a turbine, first of all, let's imagine we don't have that plate. We just have V wind. So the homework problem would be you don't have this plate at all. You just have V wind. You have U. Actually, you don't even have U. You just have V wind. And he said, draw the plate for me. So you need to decide, do I need to take him up or down? And he can go up or down, but the plate will look different if he's going up or down, right? So if we make him up, he's going to move up, then where is V would be? It has to be like this, so that V plus U, V relative plus U equal V absolute. V relative plus U equal V absolute. That is the velocity diagram equation. V absolute is V relative, which a lot of books call it W, plus U plate. Okay. So now the plate, the airfoil in this case, he should be aligned with the V relative N, right? He need to be aligned with V relative N. And so when the plate airfoil see a velocity like this, he will generate two forces, drag force and a lift force. And the lift force is normal to the V relative, right? And the drag will be the direction of V relative. That is the definition of the lift and drag. When you hit an airfoil, a wing, a propeller, you hit it with a V relative. The force normal to V relative, we call it lift, and the force in the wind direction, the relative wind direction, is called the drag. Okay. Now this guy is planning to move up. That's the direction we are designing it for. So if he's gonna move up, he need a torque in that direction too, right? We need a torque that will take the plate up in the direction of the velocity. The torque from, not from the plate, but the torque from the wind. Meaning, I say that what I'm trying to say is that the wind need to put that force to resist the torque coming from the generator. Make sense? So since we need to generate a force or a torque going up, does the lift help in making that force up stronger? Yes, it does. See, the lift can be divided into two components. One that's axial and one that is tangential. Let's call this L theta and let's call this L axial. So L theta is the one that will help push the plate up. And L axial, what does it do? What does L axial do for us? Anyone? Help. What does L axial do? Anything useful? No, nothing, right? It's basically pushing on the bearing. So this L axial is probably gonna make the thrust bearing, load is harder, right? So you need to have like really good thrust bearing so that when you push on them, they still manage you to make them rotate. Now on the drag side, the drag can also be split into d theta, tangential direction, and d axial. Does d theta help in generating the torque, the required driving torque? Does it help? Anyone? Does it
No.
help? No, it does not. So torque never really help, except for Viking ships. If you are a Viking and you had your ship with that square sail, that is drag driven. So that's good, right? But otherwise, you can see how the drag is really hurting the wind turbine. So the drag hurt the wind turbine, the drag hurt the airplane wings, the drag even hurt the propeller of a turboprop, like those big cargo military planes. I used to work for one summer in multiple summer actually in Wright Path Air Force Base in Ohio, and they have those huge uh, cargo ships that will come, and you can like you can really hear the propeller so big. So those propeller generate a lot of thrust, but if you analyze the velocity triangle for them, I'm not going to do this in this course, but if I was teaching experimental fluid, we usually, when I teach experimental fluid, I make them plot the velocity triangle for the propeller, which would be exactly similar, except that the angle would be different, right? The plate need to be the other way. So, end of the story. If you want to plot the wing, not the wing, the wind turbine plate, you need to make it such that the wind hit the belly, the belly of the airfoil, because when the wind hit it this way, it will generate left in the right direction for rotation, right? So what is the other option? Rather than doing it like this, we could have done it this way. Rather than the camber is this way, if I do it this way, imagine if mirror image and the plate is drawn like this. That's how students lose points. Rather than drawing it like this, they will draw it like this. So what will happen when the wind come in an airfoil like this? He will generate lift in that direction, right? And that is not a turbine, right? That is probably a propeller when it's the other way, right? Very good. So obviously when you plot the velocity triangle on the other side, on the exit, what will happen? U1 and U2, what's the relation? Which one is bigger? U is the velocity of the inlet, U2 is the velocity of the plate at the exit. Which one is bigger, U1 or U2?
Same.
Excellent, excellent, because again, they are moving together. So U2 will be like this, and V relative 1 is coming this way. V relative 2, do you think it's gonna go the same direction, or it bounce a little bit down, or go a little bit up? Straight in the same direction like V relative 1, or a little bit down, or a little bit up? What's your fluid mechanics guts feeling is telling you? Flow going into an airfoil like this, the plate, the velocity would leave down or up or straight the same direction? Help. This is V relative 1 at the inlet. It go around the plate, and then at the exit, does it go down, straight, the same direction, or go up?
Down.
Excellent. Right? Because that's actually why it's going, giving generating that left. When you think about it, why it's going this way, it's probably because it's going down, it kick you up, right? The flow is coming like this, he need to go down so that he can kick you up. Also because of that, we just said what? The flow at the exit, he does not have a choice but to follow the, especially here, he does not have a choice but to follow the plate, right? So you would go a little bit down. So now with U1 exactly U2, and with V relative 1 and V relative 2, V relative 2 is going this way. Does V1 and V2 remain at the same direction, or does V2 go a little bit down? V2, this is V1, the velocity, absolute velocity at the inlet. The velocity at the exit has to go a little bit down,
Down.
right? Because V relative is pushing down and U is exactly the same amount. This is U1, U2 will be exactly the same amount, but the V2 will have to be a little bit down. So what that tells us is that V1 is all axial, but V2 is not going to be all axial. V2 will have a little bit of a twist. It will have a little bit of V2 theta. If it's all axial, it will leave like this. But if it go a little bit down in that plane is meaning that it has V theta. So what happened now? V1 was coming all axial, and then it leave down, pushing the torque up, right? So unlike the hydraulic turbine that we had in our homework, where you had initial twist and you leave axial, you consume all the twist. Here, you come all axial and you leave with a twist, pushing the plate in the other way, giving torque in the other way. So while V2 is leaving twisting this way, the plate is going to be pushed that way. Make sense? Right? So the velocity at the exit will end up basically swirling at the back, that the wake. And people who do simulation of those things will show you the wake of this thing and how it's twisted this way, right? So you guys know that you come axial and you leave with a little bit of rotating, right? So that should give you some idea about like how you can actually, there is a lot of improvement that can be done to those things. One of my office mate actually in Michigan, when I was a grad student, he came up with like small things that you can vortex generator that you can put just like the one in airplane, but you can put them on the plate already existing turbine plates, and that increase the performance, right? People still trying to figure out what is the best shape for the airfoil. If you actually look at the airfoil, and we will see actual drawing in a minute, you will see that it's not like an airplane airfoil. What is the difference between that plate and between an airplane airfoil? I mean, both of them get wind and generate lift and drag. You want both of them want the drag to be small and the lift to be really big, because that's what pay the bill, carry the people in the case of the airplane, generate L theta that is running the thing, and the drag is always hurting. Here, d theta is eating our L theta. We don't like it. And in airplane, the drag is why you have to burn the fuel. All the thrust that you generate is to eat this. Has the airfoil of the airplane, and the body too, of course, right? Not just the wing. But has the airplane don't have any drag, we don't have to pay thrust. I mean, it will just fly free, right? So both of them really would like to reduce the drag. So then, shouldn't the airplane wing and the turbine plate look exactly the same? What's the difference? What do you think? The main difference? What do you guys think? Should I get an airplane wing and just stick it here and make it my turbine plate? Help, tell me something different between them.
that hump not on the top side, more on the bottom side, or
No, it's more, it's actually, it's about operating condition. Think about the speed. Airplane is optimized for a cruising speed. That airfoil need to basically always run at that speed. So the shape is perfect for that speed. But the wind turbine doesn't have one speed to run at. I mean, you don't run the wind turbine only when it's like 10 meters per second. 9, sorry, I'm not running. So because that V can vary, huh? And of course you try to catch up with this, but because this is varying, then the direction will be a little bit different. So the airfoil, rather than being perfect at 10 meters per second, you want it to be okay at 5 to 15 meters per second. You have bigger, you always want it to work, right? So you will see that the inlet is like really huge, like camber, huh? Then the tail. So this way you come here, you come here, you come, any angle you come with, we are fine. We will still run. Okay, very good. So this was the tail of the like from fluid mechanics point of view. But from energy point of view, people just like to see this thing and do kind of Bernoulli equation kind of analysis. Huh? Just the same thing for the wind, for the hydraulic turbine. I mean, you can go into the fluid mechanics part and what's the angle and what's beta and what's alpha. But then at the end of the day, you can also look at the whole thing as one big black box and say, I give you this much potential energy, how much torque you are, or how much power I'm getting. And that the ratio is the efficiency. And we saw those graphs that plot the efficiency as function of the specific speed, remember? And the efficiency was like as high as 99, 97 for like Bilton wheel, and like in the upper 80s for Francis, right? And Kaplan. So the same thing here for the wind turbine. We can also analyze this from the energy point of view. So from the energy point of view, what do I deliver for this turbine? I give it kinetic energy in that big cylinder. Like this air is coming, I have an area by square, right? And I from that area, rho time the area time the velocity, that is what? That's my flow rate, right? M dot. Rho AV. Rho AV is my M dot. Okay, that's my M dot. And the kinetic energy per unit mass is V squared over 2. So this is the power. The power that is delivered to that disk is half rho A V cube, because V squared from here and V from here. So the power is function of V cube. That's why, they show you those maps all the time, because when you go from 9 to 10, it's a big deal. It's a big deal because the power is scaling with the velocity cube. So 9 cube and 10 cube. It's a big deal, right? Going 1 meter per second extra, right? So now how much of this input power is going to be electricity on the other side of the cable? The ratio between those things is kind of our efficiency. But in wind turbine, they feel they don't call it efficiency. It is efficiency, but they call it instead CP. Okay, what's CP? Power coefficient, which is power output over power input, which is efficiency, but no, we're not gonna call it. I think so we have to respect their vocabulary, right? So the power coefficient.
Salam, sorry to
Yes.
interrupt you.
No, interrupt anytime you want.
Would you mind showing me that velocity on this figure that is right now in this slide?
This one?
No, no, no. The
This
one,
one?
yeah, right here. That
Yeah.
velocity, the wind, and all those in this figure, like this explanation on that figure.
What do you want me to show you?
I kind of still got confused on this V wind and U blade and all those. I just
So there are two velocity here for the air. There is the absolute velocity and there is the relative velocity, right? So the absolute velocity is the velocity that someone on the floor will see. Someone not moving will see. That is this one. Makes sense? It's all axial and it's coming toward us. Yes?
So we are talking about the blade of the wind, right? I mean, like that windmill.
The blade of the wind, there's no such thing as the blade of the wind. There's a blade of a turbine.
Yeah, yeah.
This guy is a plate of the turbine, and I am doing a cross section of it. Like what I'm trying to say is that this guy is like really go from the hub all the way to the tip, as you can see over here. See, go all the way from the hub to the tip.
Okay.
So if you just cut in that place, it look like this, except we are cutting this guy, the horizontal one in front of our eye.
Okay.
Right? And so the wind coming toward him, coming parallel to the floor, right? This is the ground.
Yes.
And so the wind has to come horizontal, totally horizontal toward us.
Yes.
Okay. So now the plate is going to go up. Why? I mean, we can draw it going down, but it will look different. But if we decide that this is the velocity of the plate, because he's gonna rotate like this. So at this point, he's gonna go up. At this point, he's gonna go
Down.
no, here he's gonna go. When he's at the top point, where is its velocity? Anyone? What is the plate velocity at this place?
There no velocity, I guess.
No, there is velocity. Help me, anyone. What is the velocity of the plate when he's here? When he's at the highest point, where is its velocity?
At the
Anyone?
tip?
Huh?
At the tip of the blade?
I want the velocity of the tip of the plate, which way it's going. That's what I'm asking about. The tip of the plate. What's the velocity right now? Which direction is it moving? When he's at the tip. When the tip is at the top, dead center, I guess. Not dead center, it's the top place. When he's at the top position,
Counterclockwise?
is the velocity of the plate.
Counterclockwise?
Away from us, right? Yes. I wouldn't call it, yes, counterclockwise, correct. And away from us, normal to the page, right? Right?
Yes.
Yeah.
Yes, you will be shooting exactly normal to us. And when he come down on this side, on the other side, he will be shooting down. So on the other side, if we want to plot it on the other side, he would be like this. That would be his U. Okay? And he will look like what? He will not look like that. He will look like this. Make sense? Yes? And
Yes.
V would always be like this. But this time, this would be U. No, that's not going to be U. He's going to shoot down like this. And so what would be the...
That'd be flipped around the other way toward that blades on the top side, that skinny parts on the top.
You want that skinny bar to be here?
No, on the top right. Like, so the skinny part be on the top right, the fat part be on the bottom left, right?
So
'Cause if we're looking at it from the other side, I guess.
so this guy, he will always be at the end, right? And the camber, rather than basically going up like this, he would be going down on the other side, right? I mean, we just have to draw. This is not nice. I need something curved a little bit, like maybe
So shouldn't it be like,
something like this, like this. So when he go to the other side, he will be the other way. So
Oh, you mean that the curved part will be on the top?
the curved part will be at the bottom,
Or like, yeah, vice versa. I mean,
right? It be like this.
it is before it
On
will,
the other side.
yes.
Yes, very good. So this is V. It's always flowing down. Sorry, always horizontal, and the U will be determined. Are you going up, which will happen here, but then on the other side you will be going down. That would be the U. Okay, and you want the V relative to be in the direction of this guy, of the camber. So then it will generate left that will still make you rotate in the right direction, and drag, unfortunately, that will just slow you down. But that left component will always be swirling you in the right direction. It will keep you moving in the rotation direction. Does this make sense?
Yes.
Okay.
I had one question.
Yeah.
When the windmill itself moves on its axle according to the wind direction, what powers the motor itself? Is it supplied externally or is harnessed from the wind?
So for small turbines, the one that's running, say, a water pump, like in the farm, they will have this big tail over here, and that tail will always align you with that tail. Could actually big as the plate, as tall as the plate. But that tail, and usually it will have a spring in it so that you cannot snap him out. So the wind will push on it, and the spring will extend a little bit, but then he will bring back the whole farm, the whole axle again to the direction of the wind. But for the big ones, that has to move with electric motor, and that electric motor could be energy stored on board, or like energy being stored right now, you know. So
Oh, so it's basically like a big capacitor in a way.
some there is a motor that moves those big ones, and that motor need electricity. Now, would that electricity be stored, or will it be used from the network itself? Like, for example, that cable we're running back and forth, that I don't know. I don't know
Okay.
that technical part, but you need to run using a motor for big ones. You are not just gonna be swinging it in the wind because you don't have that big tail.
Thank you.
Very good questions. Wow, why really? So this will stay with us. Okay, so why don't we take a 15 minutes break, and we will come back while I'm cleaning this. All right, 15 minutes break. All right. I think we start. It was been 15 minutes. Can you guys hear me?
Yes.
Very good. And you see my screen, right? So we said that it's nice to see the plate angle and all those things, for optimizing the direction and everything, but also it's important to look at the whole thing from energy point of view. So from energy point of view, one should basically look at the output and the input, and the ratio between them is the CP, right? Power coefficient, which is efficiency. So how does the CP look like? Here, this is the CP on the y-axis, and for different shape, and the CP or all those shape is function of the tip speed ratio. What's the tip speed ratio? Omega r divided by u wind. What's omega r? This omega time r. So it's like the tip velocity. And u infinity, that's the wind pushing in it. So first thing you notice, two really amazing thing you notice on this curve. What is amazing that you notice? Two things that will like make your mouse like, what? I cannot believe that. What you don't believe on this curve? See all
The one,
different shape? Yeah, go ahead.
the one blade rotor, that got me by surprise.
Well, yeah, but it's not really practical, right? You can see that it's also the maximum thing you get is like 3 plates, and that's why they are most common. 2 plates are not really that great because of there is kind of imbalance when the plate hit the tower, not the tower, but the tower is behind the plate. So what happened is like he's like in a really bad spot. He's not getting power. So only here when he's cleared the tower, he can generate power, but here he's dead. And so that creates some unbalance. This gets less when you have 3 of them, because you have 2 driving and 1 that's not driving when he come into the bad position, right? But when you have like 50% off, that is and 1 plate, you probably think, well, that's gonna be unbalanced, and he probably will tear himself out because of the centrifugal force. But that's why they have counterweight, right? But having less and less plates make you move toward higher and higher tip speed ratio. And it's supposed to increase the efficiency, but you can see practically for practical problem, it's actually going to decrease a little bit. But you wish it can go this way. And the more blades you have, like the American wind farm, you end up with this, very low speed, right? But high
So
torque,
for
by the way. Go ahead.
So for the theoretical power efficiency, when they calculated it, what blade ratio did they take in place, or they didn't take any?
I didn't get that question. Ask that again.
So for the theoretical power curve that they have near 0.6,
Yeah, this one? Right.
yes. On what basis is that curve? Because the 3-bladed is quite close to the 0.6.
Right. So we actually gonna see that curve in a minute right now, where this come from. But what surprised you in this graph? 2 things need to really make your mouse drop. Like, what's going on? Anything that's weird that you are shocked to see? What I'm shocked to see this. Look at that. What is that? That's the maximum theoretical possible CP. And it is 59%. They are saying no matter what, no matter how good you are, a wind turbine cannot have an efficiency more than 59%. Okay? And that's based, this is called the Betz law, Betz, B-E-T-Z. And that's the guy who came up with that limit. And he figured, well, we cannot hit more than 59%. Why this is surprising? Because we just did the hydraulic turbine last week. And I remember the built-on wheel efficiency, theoretically speaking, was, what's the theoretical possible efficiency of the built-on wheel?
100%.
Yes, 100%. Good job. 100% was theoretically possible. And practically the curve that we had, the efficient again is that was not theoretical curve, that was actual curve, and it was easily above 90%, right? So why, when you run water turbine, you get 99% or 90%, and when you run wind turbine, you cannot hit more than 59%. And actually, a few years ago, there was one research team from North Africa. They said, we managed to make a wind turbine that exceed the bed slope. And it was like in the news all over the place, all over the world, basically, that they made a wind turbine. But it was completely, when you see in the next two slides, you can understand how is it possible to exceed that limit. But it's not really going to be exactly a wind turbine. So that is one surprising thing, okay? And we'll see why this is the limit. Okay. Second thing that should surprise you is this. The x-axis. The x-axis go from 1 to 10. What does 10 mean? What does this number mean when the speed is 10, or like the actual turbine, you know, the most common one that we have all over the place, it's like 7. He's saying that the tip is moving 7 times more than the wind that's driving you. Okay? So doesn't this shock you?
Does that mean the velocity?
Tell me why you're not shocked.
Do they use bearings?
Say that again.
Is it because of the bearings that is possible?
What about the bearing? If even you have the best bearing ever, like how come the wind speed is running, the plate speed is running faster than the wind? Doesn't this annoy you at all? The driven is moving faster than the driver. Doesn't annoy you?
Well, you have multiple blades, so it would have more surface area to generate the force to.
But still, I mean, I have 3 kids in front of me and I'm kicking all of them. How could they run faster than me? No matter how many. I mean, I'm the same wind driving all of them. How could they run faster than me? What's the explanation? It is running faster, right? So the explanation is because those plates are not running by drag. If they are running, if they were a Viking ship where the sail is like this and the wind is pushing on it, that sail cannot move faster than the wind, no matter what, right? But when you do it based on the left, not the drag, you can generate force and you can make the speed of the plate faster than the wind blowing on it. Okay, like sailboat. If you look at the sailboats, they can easily run faster, twice the wind that's blowing on them. Okay, and so it's really interesting to actually plot the wind and the sail of a boat. If this was a boat, you know, and I'm not gonna give you this in the exam, but I used to do it for experimental fluid. The boat would be, I need actually to draw, I need to draw this. So the boat would be something like this, right? That is the boat. And the sail would be really something like this. That's the sail. And with the wind coming this way and the boat moving in that direction and v relatives like this would be the left, which will push us forward. And yes, there is a bad direction, bad left, or not bad left, but that part will try to send us back like sideways, but it will be countered by the keel. That's another problem, another thing to fix with. But the point is, now let's make the boat go faster than the wind. 7 times faster than the wind. You see that velocity triangle? The v wind is coming this way at say 1 meter per second, and the boat is moving 7 meters per second. Look at that. What is that velocity that I'm just plotting? What is this one? Help.
Relative.
Relative velocity. So no matter how fast, that's the key point here. No matter how fast the boat is 10 times moving faster from the wind, there is always V relative, right? And all you have to do is adjust the sail for that new direction, and he will still generate a force. Yes, the force now is more and more pushing you to the side, but still there is a contribution that push you forward. Okay, so because we depend on the left, we get a component that take us forward. Okay, have we depended only on the, like a sailboat again in the Viking time, where they just have that square and the wind is blowing from behind? He cannot move any more than the wind speed. You got me? So what I'm saying is that no matter how quickly this plate is moving, there is no escaping the wind. There is always going to be V relative. All right? And so that's why, can I actually, I think maybe I stop share and then share again. Then that will clean. Okay. So, what? So no matter how quickly your plate is moving, 7 times, 10 times, you will still get a contribution. But the guys that are running with drag, like this guy, see this Savonus type, that is mainly drag type. He cannot hit more than wind speed of 1, after which, and that's the tip. I mean, the rest of the plate is moving with smaller speed. That's why he still generates some power. But at one point, when all the plates is running as fast as the wind, you get 0 power. Does this make sense? So you depend on the drag, and those guys are like cups, huh? Those are Viking ships, sails. You cannot move faster than the wind, but you depend on the left, like the Dutch turbines, you know, the traditional Ch4 or the American wind farm. You'll be able to hit 2 and 2.5 and stuff. It will still work. Very good. So then this curve, what I need from you is to be able to extract this point based or the CB based on the speed. So I say if the problem say the wind turbine is running with a tip speed ratio of 7 and it has this much dimension, find out what's the maximum power it can extract. You would say, well, it has this area and the wind speed at that place 7 meters per second, for example, or whatever the wind speed is, and rho air is 1.2. Here is the input power. Now to come up with the output power, I need my CP. So I go to this curve. What turbine did he say? Did he say American wind farm or Dutch or the 3-plate turbine? Whatever he said, I'll go there, find out the tip speed ratio, right? And I calculate my CP. Does this make sense? So now what control the U infinity? That is Mother Nature. Mother Nature will tell you U infinity in that place is this much. But what control omega? What control omega?
That's the lift, right?
Say that again.
Say the lift or the lift force.
Well, you can manipulate it by playing with the plate angle. That is correct, and you can see there's a way to make this guy rotate less or make him not rotating as fast by messing up his angle. Like you can control this pitch angle so that he's not optimized and therefore he will not run as fast. And you do this when the wind speed go really high. When U infinity is like very high and you don't want him to speed up, you basically mess him up so that he's not generating as much lift. But that's control over it. But what is like the main driving force that control omega? What do you think? Like why the plate would run at 100 RPM or only 10 RPM for the same wind speed?
radius?
No, I don't think it's the radius. What's
Like the surface area?
no,
The angle at which it hits.
no. I think that was Denver just said. No, it's not. It's not the angle. It is the load, the generator, the pump, whatever is holding the shaft on the other side. The wind is twisting the plate, and someone else on the other side holding the shaft. And like, no, don't move, don't move, unless you move me first. That shaft is connected to a generator or connecting to a stone that's crunching grain in the old time in the Dutch mill, or connected to a pump that's taking the water from the well. So the load and the gearbox connecting the two of them will make the shaft easy to turn or hard to turn, right? And so it is the job of the designer to make sure that the load with the power available from the turbine put you where in that place, right? Because if that 3-plate turbine run at higher velocity or lower velocity than this, then it will not gonna be optimized. It's not gonna extract the power the way it should be. And yes, the power is for free, like the wind is for free, but still that machine costs money. And that machine need to generate electricity equal to its initial cost in 7 years so that we can break even, kind of. So you pay $2 million for that turbine. In 7 years, you should get back your $10 million or whatever, how much money you spend on that turbine. And then after that, you'll start getting money from it. So that is a problem, by the way, in all renewable energy, that you pay, fuel is for free, but the machine costs money to install. You buy photovoltaic cell on top of your house. Yes, the sun is for free, but I have to pay $10,000 upfront to put this thing on top of my roof, right? And then for 7 years, I'm hoping to get electricity every year that I will pay for the initial cost. Point is, it's very important that the turbine generate power at its maximum efficiency point, right? And for this to happen, it needs to run at that specific tip speed ratio. Whatever the wind is, omega need to slow down or speed up so that you can hit that point, right? And you can do this by, if you have electric generator, you can reduce the torque on it. Yes, you are not going to extract the same amount of power from it, but you let it run at the optimum speed. Does this make sense? All right. So there are general classification between horizontal axis wind turbine. Those are, the axis rotation is horizontal. And those are traditional ones. The modern one that everyone is using, those are kind of weird. People don't use. And you can see, like, we will try to do a lot of modification in order to make it a bigger area, whether at the inlet or at the exit, that help, right? And look at this one. Why do you think they have 2 plates, 2 rotors, counter-rotating rotors?
The one behind it would catch the wind from the one in front of it.
Especially that the one in the front is already sending the flow with a twist, right? So then the other one can rotate the other way. Make sense? So when the wind come in the first one and it spin it this way, the flow behind it go the other way. And so that twist in the other way is perfect for the other rotor to go the other way and get that twist, use it. Yes? Very good. And then there are the vertical axis wind turbine, which not as common because they actually, there's something nice about them. What's nice about the vertical axis wind turbine? Vertical axis because the shaft is vertical, right? So what's nice about them? Can anyone say something nice about them? when the shaft is vertical? Anything? Say
You could
anything
stack.
nice.
Doesn't matter which way the wind's blowing. It's all-
Exactly. They don't need a tail to direct them. You just set them, let them sit at the plate at basically in the wind, and they will run. They don't need redirection. But what's bad about them, also here's one more thing that's nice. Their generator, which usually is very heavy, can sit on the floor. So you don't need to hang the generator on top of the tower, and the tower need to be really big and heavy, right? So the generator can sit on the floor. And that's why those things, people think those are actually more suitable for urban setting. Like on top of the buildings or something, you can set a vertical axis wind turbine. Okay. We actually, when I was undergrad, we had this guy on top of our building, our engineering building. And we went one time to the roof and we didn't understand what is that because it looked like an egg beater. I still remember looking at like, what is this? Does it look weird? But when you look to those plates, it's actually airfoil. And so those guys are like sea airfoil and they will spin in the wind. Okay. So what's nice, the generator can sit on the floor. What's nice, they don't need direction adjustment. They will run whether the wind is coming from the right or left or anywhere, right? And actually also there was I found something else also like just like 2 weeks ago. This one, yeah, February 5th. See this? Department of Energy also. Look at this one. This is exactly like what? Like this. So it's a helical, huh? It's a helical turbine, but vertical axis. And this is actually, but now rather than standing up in the wind, it's sitting in the water. So this will go down. And what's nice is the guy who invented it, he had a patent on that design. Amazingly, whether the wind or the water is coming this way or that way, it always rotates in the same direction. So isn't that nice? 1 year, the velocity diagram of that guy was actually the homework. Well, why don't you plot the velocity diagram when that plate is here and here and here as he rotates in the wind? And how does, no matter which way whether the wind is coming from the right or the left or the top or the bottom, you always rotate in the direction of the leading edge. So the airfoils, each one of them will just rotate with in the forward, kind of. Okay. So what I'm saying is, so what I'm saying is, so if we imagine, I have to click on this. So what I'm saying is that if we imagine like a circle like this, and the airfoil is here and here, like this, and here, like this, and here, like this, and the wind is blowing this way, he will always rotate this way. And whether the wind is coming this way or top or right, he will always rotate in that direction. How do we do the velocity diagram for something like this? This is sound like a good homework. So I will tell you, plot the velocity diagram here, 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 or here. How do you do that? What do I need? I need the U, right? And I need the V relative. This is V absolute, right? The wind is coming this way, V absolute. So let's look at this guy. So where is the U going? Up or down?
Up.
Up. So here is U. And so if this is V and this is U, which way W would be? Should W go down like this or go up
Down.
like this?
Down.
Down. So this way, W plus U equal V. And if W is this way, which is the direction of the drag? Drag should be in that direction. That's easy. That's the drag.
Yes.
But now the left, is he up or down?
Up.
Is the left point up or down?
Up.
Excellent. Excellent. This is actually not easy. People get confused. So it will be up. And again, look at the left. He's helping because he has a component L theta that is in the direction of rotation, right? Yes, he has a radial component that doesn't help, but he has a component that's pushing. And the drag, the opposite. The drag has a component that will eat from our L theta, right? So you are hoping that that airfoil is such that the left is really way bigger than the drag, right? And now when the wind is coming this way, on the back side, because the wind keep going everywhere, the wind, let me draw the wind, my wind is red. The wind is blowing this way. So which way is the plate, up or down?
Down.
Down like this, right?
Yes.
That's the plate. And so which way is W? Is it going up or going down?
It's going up.
Excellent. So this way, W plus U equal V, right? And so when W is going this way, which way is the drag? This way. And which way is the left?
Towards the left.
So the left should go up or down? Because the left need to be normal to the force, the wind direction, right?
Yes.
So the drag is in the wind direction, the V relative. Again, we don't care about V absolute. This is the drag and the left. Should it go up or should it go down?
So
Go down.
go down.
Go down, right? Should go like this, right? So now how do we tell? So basically the airfoil, you need, in order to find out the aerodynamic force, it's much easier to guess where is the total. The total aerodynamic force. Is the aerodynamic force is going to be like this or like this? Right? Actually, sorry. If this was the left, then the aerodynamic force would be like this. The total. The total is the left plus the drag plus the left. So you need to tell yourself, if I am pushing this way, will he get pushed this way or will he get pushed that way? Right? So he will help, right? But here it will be all drag, and that will be very useful. Here, when the wind is going this way, this will be all drag. There is no left, and that doesn't really help. So he had this region when he's not really helping. Okay, but in general, he was always getting a force that will turn him this way. And amazingly, whether the wind is coming this way or coming from the right or from the top or the bottom, you will always see that he will always turn clockwise. Okay, and that's the deal with this guy too. Okay, so each one of those airfoil, now why they are helical? Why they are doing them in helical direction? Like the plate is not straight. The straight one is called H rotor, where all the airfoil are basically sitting straight. You know, if the airfoil is like this, and the other on the circle, the other one is basically like this. You know, this is called H rotor. But when they make it with a twist like that, why do you think that is the case? And it has to do with that velocity triangle that we just drew. Because there are places in the cycle that the airfoil is not helping. He's actually being slowed down because he's flying against the wind. So that's not helping, right? So when he's flying against the wind, he is a liability. He's hurting us. So when you have them straight like this, you have a whole plate that is really hurting the cycle. And so the turbine will be like tuck, tuck, tuck. Every time one of the plates come to that place, it will be a problem. But when you make it helical like this, what's the advantage? Anyone?
Well, in that particular spot, I guess it would be thinner or maybe twisted a certain way to where it's not creating so much resistance.
There will be, when it's helical, there is always one spot in the good place and maybe one in the bad place, but it's continuous. There is continuous operation. Huh? Like you're always having the other plate in a good place and the other one maybe not as good, but there is no tuck, 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 tuck. It's always shh. Huh? The whole, it's like, like if your family has like 3 children, 3 kids, and one of them is like sometime get in trouble. Every time you get in trouble, the whole family go down. But if you like, I mean, that's a horrible example, but if they like always go continuously, like he's always in bad shape and the other 2 guys are always in good shape, then the family goes smooth. There is smooth operation, kind of. So with a helix like this, there is always one section in the bad position, but the rest are in good shape. The rest of the airfoil is really in good shape. And so they wouldn't suffer as much. I'm gonna stop and then share again. All right. So anyway, they are saying basically that they are installing this for a place, 35 kilowatt. You can see it's not really a big deal, but tiny Alaskan village, and rather than driving the natural gas to them or giving them gas for their diesel generator or gas generator, something like this, no matter how expensive it is, it actually makes absolute sense to run it. Okay, does this make sense? Very good. This guy, by the way, Ted, is working for solar voltaic now, and he actually took the course a few years ago, and now he work for Francis Solar, which is part of Tesla in Tulsa. And their job right now is to build as many charging stations for electric car as possible on the highways. It's funny, when he got the job, he told me like basically the only exposure to solar energy was in that course. So maybe one of you will get a job in renewable energy, and this course would be the only thing that you would benefit from. So hopefully the course would be useful for at least one of you. All right. So now, all those turbines, horizontal or vertical, what is the theoretical limit? Why Betzlow said it's 59%. So he's doing it in these pages, in those next 2 pages, just based on energy conservation point of view. Okay, so this is Bernoulli equation between B inlet over here, and going to this. B1 is just before he goes through the plate, and then B2 is just after he went after the plate. That's why I'm saying that in that sketch in the book, B1 should be here and B2 should be here. So he's basically building the pressure just before the turbine, and then as he goes through the turbine, his pressure drop, just like what you expect going through a compressor. Before the compressor, your pressure is low and you jump up, the turbine is the opposite, right? But while the pressure drop during going through the turbine, the velocity on the other side is kind of continuous, right? There's because of the flow rate, kind of. And so he's saying that and of course, once you leave the turbine far enough, the pressure will recover again and you get the regular pressure, right? And so he is trying to figure out what is the optimum, what's the maximum power we can get. So what control the power that we will get from the turbine? It depends on how much did we reduce the velocity. kinetic energy. We are converting kinetic energy to mechanical power. So originally, we have C. That is the velocity at the inlet. That's why the power at the inlet is half rho A C cube. Half rho A, the velocity cube. And he's calling the velocity C. And then he realized that at the end, he's going to slow down the velocity. Otherwise, how did he generate power? The way to generate power is to slow the kinetic energy, eat it into mechanical power. So he's going to slow it to C multiplied by 1 minus B. What is that B? Is it 50%? Is it 30%? So B is a fraction. We'll see what is the maximum or what's the optimum B. And you may think that, of course, I should make it go to B should go to 1, meaning that the exit velocity should be 0. That is the maximum power, right? Right? From energy point of view, if you want to make something that's 100% efficient in harvesting something, you should eat all of it, right? Like the consumer come into your shop and you want to harvest all his money. So he leave with 0 money. Then your efficiency of earning is 100%. But so the wind come to us and then it should leave with 0 velocity. But the problem is that if the consumer leave with 0 velocity, the consumer leave our supermarket with 0 money, he will not be able to get an Uber to go away. And so he will stand at our door, not leaving. We didn't work right this way. So it's almost the same idea. So if you kill all the wind speed at the exit, the wind is not gonna leave. You still need velocity to let it leave. Okay? And that point is what will, as you will see in the derivation, the fact that we need the velocity to still leave, that's what will turn our efficiency to 59% max. So one of you right now should jump on me and say, well, how come you didn't do the same thing for the wind turbine? For the hydraulic turbine. How come with the built-in wheel, you said that the maximum velocity, the maximum efficiency was 100%, and you said that the velocity at that scenario V exit was how much? For a built-in wheel with 100% efficiency, V2 become, help.
V by 2.
V2 was what? How much?
V by 2.
No, that V1 U was V1 over 2, but V2, the velocity at the exit of the plate was
Be the same coming in, right?
no, for 100% efficiency. V2 was, you want me to pull the lecture from last week? V2, if we have 100% efficiency of a hydraulic turbine, V2 should be, V1 is the inlet velocity coming from the high dam, and V2 at the exit velocity should be
0.
0, of course, 100% efficiency. You need to kill all the kinetic energy. So we said that, and you guys did buy it. And yes, it is correct. You can make it go to V2 0, and you get maximum efficiency for a built-in wheel, 100%. But here, I'm saying no, V2 cannot be 0. You cannot leave with 0 velocity. How come it was okay for that to happen in the hydraulic turbine, but in the wind turbine, when it's air, I say, no, you cannot do that. Think about this. If you have the answer, you get free homework problem. Email it to me. Why the discrimination against wind turbine? The hydraulic turbine was allowed to have V2 equals 0, but the wind turbine, no, we can't. All right, let's continue with the derivation. So he's the Bernoulli equation, and then this is just the momentum equation. What is the momentum equation? The force is equal to m dot v out minus m dot v in. That's what you're looking at over here. Okay, and so he applied the momentum equation between here and here because there is no external force, and he's applying the Bernoulli, the momentum equation between here and here. Okay, because again there is no external force between the two of them. and then just a bunch of mass, and he is saying then at the end the force on the on the on the turbine, P1 minus P2 times the area, you get that, and from that he's saying that, well, that force is the force that the turbine experience. Where is it coming from? It's coming from the wind, right? I mean, who else is pushing the turbine plate? The wind. So when you apply the momentum equation between the force and the momentum at the inlet, C, m dot C, and the outlet, m dot C 1 minus B, which we don't really know B. We don't actually know two things, by the way. We don't know B. We are trying to find out what's the optimum B. And again, it's not 1. We don't want to slow it down to 0. Otherwise, the wind will not leave. But we don't know what's the optimum. And we also don't know A. What is A? The wind is starting with a C. Slow down to C times 1 minus A, and then slow down to C 1 minus B. So first, he's trying to figure out what's the relation between B and A. And then he will try to optimize B or optimize A, one of them. I mean, one of them should be the variable. And that once you find out what is that optimum value, you'll be able to find the corresponding optimum power extraction, right? So by doing Bernoulli equation and just momentum equation and this derivation, he figured out that actually A is B over 2. A is B over 2. So if you're going to slow down the wind by 80%, then over here it will slow down 40%. So it slow down 40% just before the turbine, and then continue slowing the rest later on. So now what is A or B? One of them. So then we can know the other one, and we can find the power. So he is finding out what is the energy lost between C and between C1 minus B. Okay, and he found that energy lost is the energy that he's going to extract, right? And then he differentiate that expression, that energy that he's harvesting, with respect to the variable that control it, which is A. So dE by D equal to 0, and from that he figured A is 1/3. So the wind slow by 1/3 optimally before the turbine, and 2/3 before it leave. Okay, and that this is the maximum power you extract. And that, by the way, what's the relation between the power and the energy? Anyone? What's the unit of the energy?
Joule.
Joule. And the power, joule per second.
Yeah.
Right? So the power is the rate of extracting energy, right? So the power is m dot rho eV. And the energy per unit mass is half V square. Half V square, that's kinetic energy per unit mass. Right? Very good. So here is the power output, and he divide this over what was available. What's the input power? Input power, that is what was coming here. What was coming here was the half rho AVQ, or half rho AC square, right? Because you call it C. So half rho ACQ. So the ratio between those two guys is 0.59. That is the CB max. So the CB max that Betts come up with, this 0.59, is basically just based on, I cannot let the wind die at the exit, otherwise it will not leave. So I am between, the power is m dot kind of delta, m dot times delta what? Half rho V square. The change in half rho V square, or half V square. The change in half V square, but m dot that's going through, that also be affected by the velocity through the plate. Okay, and that velocity turned out to be related to the velocity at the exit. So you kill this guy, and you're gonna kill the flow rate that's going through, and I get 0 power. Does this make sense? So still, it's what should really be amazing and puzzling for you right now is why this make all sense. We get it, but why did we manage to let it go with zero velocity at the exit for the water turbines? Why was that possible? Okay. And by the way, maybe a hint, that helical turbine that we just saw for the water, that would be like a wind turbine. That will also have 59% efficiency. It cannot go to zero. So it cannot go to 100% like the built-in wheel. So why this one is treated as if it's a wind turbine? What is the difference between those two scenarios?
In wind turbine, all the
No. Keep it for the free homework problem. You email it to me unless you have a question, but don't answer.
okay.
Keep it for your free homework. So this is 0.59, right? But actually, also the real limit is not this. The real limit is actually this, and this is coming from the fact that this guy also has to twist, like when all the turbo machines, the velocity at the exit need to twist because the machine rotating, so the flow coming straight. At the exit, he need to twist. So the exit velocity had to have an extra twist component that even slow it down more when it comes to m dot, because m dot is only based on the axial component. So if you twist at the exit, that extra velocity need to be added, which even slow you more down when it comes to energy calculation, right? So that is the curve that all machines are trying to approximate or trying to hit. Okay. So then what is with the group from North Africa? They were in Tunis, I think, Tunisia, and they said they created a wind turbine that exceeded the built-in, exceeded the Betz law. So their efficiency is more than 0.6. Well, when you read about them, their disk, their design was like a disk in the wind, and it was kind of wobbling disk. So you can immediately realize that they don't have the same problem that we have. What's the problem? That we need to send the wind through. They are not sending the wind through. They are basically kind of letting the wind go from the side. And they are kind of like sending the air out on themselves by this motion. So they are kind of like scavenging their way through. So because it's different configuration, then you don't immediately think, they are like crazy and they wouldn't hit Betz law. No, it's possible if we analyze. I couldn't find the exact design, but the only thing that I remember reading is that it's actually a disk and it's wobbling in the wind. So I immediately realized they are not really totally crazy. That can work. But if you send the flow through, this kind of analysis will be applicable, and you are stuck at 59%. Okay. So now, since we are stuck at 59%, the only way to extract more power is to make it bigger, right? So if with efficiency 59%, if my turbine is like this, I will get this much. But if I make it 10 times bigger, I get 10 times the more power. And also with the economic scale, it makes sense to make the plates really big. So you can see how they build those plates. See the guy sitting in the mold, right? And of course, moving it over the highway is a big deal, especially in Europe where the streets are very small. At one point, whenever I used to go to Oklahoma City, I will always see turbine plates moving on 35, right? Was it 35? Yeah. You always see turbine plates moving in the highway, I guess, going from Dallas to Kansas and stuff to install it there. And so people build really huge wind turbine. This one, how much is that? 7.5 megawatts. 7.5 from one turbine. Okay, this is not the most common one. The most common one is like 2 megawatt, 1.5 megawatt even, but this one is 7.5 megawatt turbine. And look at the plate, what I told you before. See how this is what we call this. What do you call this edge? Leading edge. And what do you guess? Anyone?
Drag edge?
The trailing edge, right? So this is the leading edge, and this is the trailing edge. And of course, this is the tip, and this one is the hub. This is the hub, and this is the tip, right? And so one thing we notice is that radius is so huge. And so omega r here, which can hit, hopefully, what's the magic number? What should be the tip speed at that point?
7.5.
7.5 times the wind speed, right? So whatever wind this thing is designed for, if this is running in 10 meters per second wind, this guy needs to be running at 75 meters per second. But this would be a different u. Why? Because although the same omega, but different radius, right? So because the velocity triangle is having different u at from here, from here, from here, the v relative with the same v absolute. So here's v absolute, here's my u. So u at the tip is going to be this much, but at the hub is going to be this much. Big at the tip, small at the hub. So v relative would be like this at the hub, and this at the tip. And because of this, you see the twist. You see the twist at the plate, right? So from the hub, it's as if the wind like has the v relative is coming very small, so he's very small twist. But then at the tip, he's like this way, right? You see how he's like, he starts like almost normal to the wind or like in the wind direction, and then at the end, he become as if he's moving in the u direction. And also one thing you notice is that look at the leading edge, how big it is. How like really big, right? Why? Again, because like even with a little bit variation in v relative, that plate is ready to go. Okay, very good. So there is those big machines were not gonna run for any small velocity, right? I mean, all the bearing and the stuff in the generator, it requires a minimum speed to run. So when we look at the power curve coming from this turbine, it looks something like this. That's the power curve. So the first velocity that he will start in, that's called the cut-in speed. So let's call this what, 2 meters per second. So anything less than 2 meters per second, this turbine is not going to run. And then once the cut-in speed is achieved and he will start running, of course, he's not going to extract that much power, right? But as the wind gets higher and higher and higher and higher, he will get the maximum power. What is the maximum power for him? 7.5 megawatt. Okay, so that speed where he achieved that maximum power or rated power is the rated speed. Okay, so now once you hit the rated speed at say 16 meters per second, if the wind increase more, what will happen? You can get more power from it, right? But the generator, the bearing, everything in that machine is designed for 7.5 megawatt. That poor generator over here cannot handle. Here's the generator, right? So all those guys in here and the electric and the wire cannot handle more than 7.5 megawatt. So what do we do with the wind? With the wind hitting more than this speed, when we go to 20 and 25 meters per second, what should we do? We do what?
Cut it off.
Yeah, not cut it off. The end is this one. This is the cut out speed. So the cut out speed at 25. And when it hit this maximum, like the wind has to, the turbine has to stop, and they make it stop, and it will not run, so that it wouldn't really get damaged. But between the rated and the cut out speed, between V rated and between V cut out, what happened here? What happened here is that more and more wind is available. So you can make more and more power, but you don't want to. So what do you do, your plate? You mess up the pitch angle. Using the pitch control, you can change the angle so the plate actually doing worse and worse. But because the wind power is more and more, you will still maintain the same power output. Does this make sense? So when I divide the output power, this is the output power, right? The power that's available from the wind by the input power, which is what? What's the input power? Half rho A V cube, that's the V. So if I want to say, what's the input power when I'm 10 meters per second? You would say half rho, which is 1.2, time the area. Where is the area? Rotor diameter, 127 meter. You see that? Guys, you see 127 meter in the specs sheet? So that is the area of the rotor, huh? The rotor. So at this speed, the input power is half rho AV cube, and the output power is how much? Anyone? Over here, what's the output power?
3.8 megawatts.
Yes, 3.8. That's a good number to think. Yes. So if I divide 3.8 over half rho A, which is whatever the diameter is, 1.7, I get what? What is that division will give me? Output power over half rho AV cube. I get
The CP.
the CP, and that is the CP. This curve is the CP, okay? The bar coefficient. And you read the bar coefficient on this axis. So you can see that originally the CB is 0. Why? Output power is 0. And then the CB climb up very quickly, and that is like the perfect CB. And they are hitting CB of what? 0.48 or something? Huh? That's the maximum, this 0.48. So let's say you cannot hit more than 59. Well, they are doing 48. But considering this is not just aerodynamic, this is aerodynamics and bearing and generator. I mean, this is actual power coming from the cable. So it's eta electric time eta mechanical time eta electromechanic and eta aerodynamic. It's a bunch of efficiency that's keep eating from you, right? So that's pretty good. But then why does it start to drop like this?
Because your output is more than your input.
Because you're outputting more than the input? No, the opposite. You are and at that, from that point down, you are messing up your plate on purpose because you want to slow down the plate. You don't want to extract all the power. Isn't that funny? So why would they do this? Because they want to extend
The life of their machine.
the range of operation. So when you get a wind turbine that run in your site only 1 day per year, that is not really a great idea. You want the turbine to run all the time. For the wind turbine to run all the time, you need to have a big range between, especially between V rated and cut out speed, right? So you want the turbine to run a lot of days. And because the wind change a lot, you wanna have a bigger range, and that's come with all that control. So this is a little bit smaller one, right? So 300 kilowatt, but they all have the same, more or less the same trend, same curve. Here is the bar curve, and here is the CP. Okay. So how is that related to that curve? Well, that curve will run. You will get that point only when you run at the optimum speed. Okay, that's the 0.48. That's what they managed to get. when they are here, right? But then after that, wind is available, but it's too strong for your generator. You cannot generate more than 7.5 for this guy. And when you go to a smaller other model, the 300 and 300 kilowatt, smaller generator, smaller cable, smaller everything, probably way cheaper turbine, they cannot generate more than 330. So as the winds start to climb up more than 10 meters per second, they start messing up their plates so that CB sucks, but you maintain the rated power. You sold this saying, here's a sticker. This is generating 303 kilowatt, 330 kilowatt, and it's cost $100,000. If you want to get the bigger one, you have to pay more, and you have to build bigger tower, and you have to get bigger plates. Make sense? So this curve, by the way, is over here in the table. Okay. So you just read the wind, you can figure out what is the power output. And you can see how the power output, once you hit the rate speed, it just remains constant after that. Until 25, that's the cutout speed, and they wouldn't run after this. You can see how the CB is changing. Does this make sense? So the problem in something like this, it depends on you understanding or being able to extract data from this curve. So a lot of students get messed up with that CB. Why does the CB is not constant, for example? And how did you get this CP? You get it from dividing B output over B inputs, right? So now we don't have time to do this. This time we'll steal a little bit time from the next week for talking about this, but you need to know that the wind is a distribution. Like when you measure the wind in Tulsa Airport, it's not we're gonna stay at 10 meters per second all the time. It will actually have a big range, right? And because of this, we need to match the wind speed in the site with the wind characteristic of the turbine. So when you put the two of them together, you may find out that your turbine run at full power only, say, 30% of the time. That sucks. So I'm buying a 7.5 megawatt turbine, and it will never generate 7.5 megawatt except for only 2 months per year. Then I did a really bad matching. So they need to match. You need a turbine that have a range that consume or basically is exactly what you have, or a lot of what you have in the site. Does this make sense? You want a turbine that have a range that match the site. Otherwise, you have the turbine, but the wind is not there. Correct? All right. Thank you so much. Questions? All right, perfect. Thank you. I'll see you next week.